Our third speaker is going to take us to a very high-profile case study, and David Hyndman is professor and chair of Department of Earth and Environmental Sciences at Michigan State University, and his research interests include quantifying the impacts of changes in climate and land use on water cycle using process-based models, and developing novel methods to characterize aquifers that store and transmit water supplies critical to human and ecosystem health. So a particularly unique aspect of Dave's research activity is that most of it's conducted with interdisciplinary teams, as we'll hear about today, that spans hydrogeology, geochemistry, microbiology, geophysics, civil engineering, ecology, social science, and Chinese food cooking too, I think. And I will add that David's one of the most well-known international numerical analysts in hydrogeology, very innovative, and we're glad to have him here today with us.
So I'd like to begin by thanking Thomas and Dave for the invitation today, and also for the leadership in pulling this conference together. It's just fantastic to see everything from growers to scientists to people in government in the same conference talking about these important issues. What we'll talk about today is mainly work that we've been doing in the High Plains Aquifer, trying to synthesize a wide range of data with process-based models and understanding how these systems have changed through time, and then some projections of what's likely to happen with climate change and different possible management options. I'd like to thank my co-authors, especially Anthony Kendall, who's in the room, who's done a great deal of this work, and Bruno, and our graduate students, and also our funders, the National Science Foundation and U.S. Department of Agriculture. So a quick outline of the talk. We'll just briefly motivate why we're looking at the High Plains Aquifer. I'll then move into some regional climate modeling where we developed a new irrigation module to really incorporate that key aspect of the water cycle. Then I'll talk about the full energy and water balance hydrologic simulations that we're doing in the central High Plains as a broader look. We're doing the whole High Plains Aquifer, but I'm zooming in. I'll then look at some synthesis of crop yield and production data in the High Plains Aquifer. And finally, I'll end with some crop model evaluation where we're looking at impacts of climate change plus declining water levels on the expectations for future crop production. So why study the High Plains Aquifer? Well, it is the largest aquifer in the United States. It's an ideal region to study the impact of human activities. There have been dramatic declines in water levels. So if you look at this plot and you look at especially the central and southern High Plains, basically from Kansas down into Texas, you see declines in saturated thickness up to about 75%. I mean, that's just dramatic. This is not a small change in a system. If you look at that in a different way and you basically pull all that data together, the plot at the top shows a decline of about 400 cubic kilometers in water. That's the actual decline in storage, not the actual use. Now, of course, if you follow this latest report, this really isn't an issue because all we have to do is drill deeper. I beg to differ. But the interesting thing about this system is that if you look at the northern High Plains, which is the yellow line, overall the northern High Plains is fairly sustainable. There are certainly parts that are not. But you move to the blue, which is the central High Plains, you see a massive reduction in the water volume through time. And even worse, the southern High Plains, not surprisingly being in a much more arid and hot region, has even more significant problems with about 50% overall reduction in storage. Compounding the issue is climate change. We all know climate change is occurring, and if you look at the left plot, it shows by the end of the century, the projections, this is the CMEP 5 RCP 6 scenario, the temperatures are projected to increase by about 3 to 4 degrees Celsius, which will increase evapotranspiration. On the right-hand side, we see something interesting. So this is a proportion. So the blue areas will get about 8% more water, and the southern areas are going to get about maybe 9% less water. So what's that mean? It means the areas that are already somewhat sustainable will get a little bit more water. The areas that are already highly challenged are going to get less water if these projections are correct. That's a real concern. So what is happening as a result of this and various management changes? Well, you look through time, and if you saw Anthony Kendall's talk yesterday, you'll see there have been dramatic changes in irrigation technologies through time. So the color coding around these show, so flood irrigation is red. Look in the bottom plot from the early 90s until about 2015. You'll see that flood irrigation used to account for, say, 40% of the irrigation, and now it's down to almost zero. The big thing that you see is there's a shift to center pivot in the early 1990s with that basically the green, and then in about 97 or so you see most of that switched over to this LEPA technology. So much more efficient irrigation technologies. That's one of the big responses to significant shifts in water availability. So what we're doing in several projects is we're using coupled system models. So we think it's really important to bring together models from different areas, so climate models, hydrology models, crop models, and socioeconomic models, and run these things together to help understand how these systems work. We can't work in a vacuum. You need to work in these big teams to understand these systems. So one of the first things I'll show you is some new work that we did developing a new irrigation algorithm within the WRF regional climate model. We were originally a little bit surprised that in this, basically the standard model that's used, there was no irrigation model. And if you think about the importance of irrigation as a driver of what's happening with the water system, if you don't incorporate that, you're missing a big part of the water cycle. So I'll show you that in a minute. We're using a crop growth model written by Bruno called SALUS, which basically can explore a whole range of different management options and understand implications of climate change, land use change, and management. A model written by Anthony Kendall, the Landscape Hydrology Model, which has an irrigation module. We basically do a full energy and water balance simulation of the whole High Plains Aquifer to understand these systems. And then socioeconomic models. We're looking at things like irrigation adoption. So why do people adopt these technologies? And how does that spread through time and space? So first, the climate modeling piece. So what we did is we simulated for the entire continental U.S. the impact of irrigation. So the first thing we had to do is use remote sensing to say where does irrigation actually exist. We then run a model with and without irrigation and say what's the implication of that on climate. So what you see here is the regions that were simulated. This is a dry year, at least in the central High Plains and the whole High Plains. And what you see is the big areas of irrigation across the country. Obviously, the Central Valley of California stands out. You've got the High Plains Aquifer. You've got a region up in basically Idaho up through Washington and the southern Mississippi Valley. So what impact does this have? So one of the things that happens is, not too surprisingly, if you pump a bunch of water out of the ground and you evapotranspire that water, downwind areas get more precipitation because you put more water into the atmosphere. So you see the eastern U.S. gets a significant increase in rainfall, and a few other areas do as well. A little bit more interestingly, the temperature actually changes, and actually rather substantially. So if you put a bunch more water into the atmosphere, you have more clouds, and you actually cool areas like the eastern United States. And some of the areas out west actually get a little bit warmer, partly as a result of changes in circulation patterns. So these are big implications of these water withdrawals across the country and, in fact, across the world. So now moving on to the Landscape Hydrology Model. So this is a full energy balance, water balance code. It's process-based, fully distributed, and we simulate all these processes hourly across large regions. And the idea is to have a code that we don't have to calibrate, because if you calibrate codes like this, then it's hard to say what's going to happen in the future. You actually have any reliability with that. But if you can actually run it based on this huge amount of data that are available, and it represents what's happened, you now have some realistic simulation for the future. So what we do is we pull together widely available climate data, remote sensing data, soils, and GIS data, and then we compare it to hydrology data across the region. So as I said, I'm zooming in on the central High Plains. We're simulating the whole High Plains, but it's too hard to show that here. So just the central High Plains is about 385,000 square kilometers, and for this particular simulation, we're using 1 square kilometer cells, and we have three-dimensional representation. One of the really important data sets that we have to pull into this system is the soil data. So the Surgo soil data is a very fine resolution data that tells us what the properties of the soil are. What do we most care about for the hydrology? It's the hydraulic conductivity. So we basically had to develop algorithms to take this data and fairly seamlessly pull this into hydraulic conductivity across the whole region. We also use remote sensing data from NASA. So this is data coming from the MODIS sensor, leaf area index. So effectively, every 8 days, we get 1 kilometer resolution data that started in about 2000. So the model ingests that information every 8 days, talking about the change in the actual leaf area index, so basically the amount of leaves from the ground to the atmosphere. And that, of course, is really important to drive the transpiration function in the model. One thing you see if you look across the region is red is low leaf area index, so it's much drier out to the west. You move out to the east, it's much wetter, so you have much more higher leaf area index. But across the central high plains, you see these blue areas popping out, and those are areas that are irrigated. We use a variety of sources for precipitation. We can use gauge data and interpolate that, but in fact, one of the best data sets is NLDAS or some other data assimilation product that brings in the data from gauges plus things like the NexRad radar system. And again, you see much drier to the west, much wetter to the east. It's a factor of 2 to 3 in precipitation. We then simulate in an hourly sense what's happening with things like evapotranspiration. This is a model that actually has irrigation embedded. And this is just an average for the 2008 to 2014 period in centimeters per year. And not surprisingly, you see that same function that it's wetter off to the west, so you have higher evapotranspiration. There's more moisture available. Out to the west, you see much lower. But again, you see those sort of brighter blue spots where irrigation is occurring. And very importantly for this group, what's happening with recharge. So how much of the water that you put back on the ground is getting down to recharge, and how much precipitation that falls is getting down into the subsurface, below the root zone. And so this, again, is an average in centimeters per year across that same time period. And you can see that there is, in many of these areas, there's actually irrigation return flow in areas that are fairly arid because a lot of water gets applied to many of these fields. So now I'm going to move on to some data synthesis that we've done and recently published in Science of the Total Environment. And here we're looking at what's happening in yield across the high plains. And the top plot is corn, where the dashed line is irrigated, the solid line is non-irrigated, and there's some trend lines on both of those. And one of the first things that jumps out, if you look at that top plot from 1970 to 2014, is you see pretty dramatic increases in yield through time, both for irrigated and non-irrigated, at least in terms of corn. Well, there's been a lot of advances in corn technology, new cultivars, new management, and so that ascribes a lot of that increase through time. The other thing you should notice is you have about a doubling of the yield for irrigated versus non-irrigated. So it's incredibly important if you want to maintain yield to have adequate water to irrigate. Now, if you look on the lower plot, this is wheat. Again, the solid line, non-irrigated, and dashed irrigated. So you do see significant increases in the irrigated agriculture, and that, again, is mainly due to technology. Now, the non-irrigated stays fairly flat. There haven't been the same level of advances in cultivars and such with wheat. Well, what about changes in acreage? Are people planting different crops or doing more irrigation? So again, the top is corn. You see dramatic increases from the 70s up to about, say, 1980, and then still substantial increases all the way to, say, about 2010. Now, if you look at the proportion, so look at how high that irrigated corn line is to the total, most of the corn in this region is irrigated. So the Central High Plains is fairly arid, so most of it ends up being irrigated. Now, you see a fairly different story if you look at wheat. So wheat production has been declining overall. The wheat acreage has been declining from about 1980 to current. And that is basically, a lot of that is shifting over to corn. Now, in the lower part of that plot, the irrigated wheat, that stayed about the same. So a lot of the areas that were doing irrigated wheat have stayed in irrigated wheat. So we wanted to do some analysis of this data a little bit further to say how much crop do we get per drop of water we actually put on. So the top plot is the change in yield with irrigation, and this is in kilograms per hectare. So if you compare corn, you gain about, say, 4 megagrams per hectare, whereas with wheat, it's more about 1. So you actually gain a lot more if you add irrigation to corn than you do to wheat. One of the good things you see, if you look at the middle plot, is the water application has substantially declined, basically per acre. You're basically putting on a lot less water for both corn and wheat between, say, 1970 and 2010. So again, substantial advances in the technologies of irrigation. And then the further analysis of that is the yield of water per actual applied, the yield increase per applied water. You see these, again, substantial increases in corn, moving from about 5 up to about, say, 16, and not as much in wheat. The final sort of synthesis of all this is, does it make sense to actually irrigate on an actual economic sense? So how many dollars do you gain per hectare per millimeter that you put water on? And corn is basically going to say about 2 to, when you see the big spike in corn prices there around 2009 through 2011, you see then you're getting up around 4, and now it's coming down because of the prices of corn. So basically it's integrating all that information. And then wheat is closer to about 1. So the final piece is looking at crop modeling and understanding, first of all, what's happened in the past, and then project this forward with different climate change scenarios. So the left part of the line, basically left of that dotted line, is a comparison between data and simulation. And there's a grayed area which you can't see. But what you see is the simulation is black, the data from the USDA is green, and this wasn't calibrated, so you're seeing the model is doing a good job of representing the changes in yield, in this case irrigated yield, through time. Then we go into the forward projections for RCP 4.5 in blue, 6 in yellow, and 8.5 in red. What you see is that the lower emission scenarios, which in reality are not so likely, you see a leveling off of yield through time. More concerning is if you have RCP 8.5, the high emission scenario, you see pretty dramatic declines in yield. Now I should note, these do not have any kind of adaptation. So there's not using different cultivars as you go forward with time, which obviously farmers would do if they see the potential for this occurring. Well, this is only one piece of the step. I'll come back to this in a minute and show you what happens to production. But I also want to show you what happens with wheat. So you don't see the level of decline of wheat. Well, wheat's a C3 plant, and CO2 fertilization is actually pretty important for wheat. So the model actually accounts for that CO2 fertilization, so you can actually see increases in wheat yields to the future as a result of climate change. Not to say that we should do climate change to improve our wheat yields. Now, the yield is one piece of it. Now, as I said, we have dramatic declines in water levels, and we're already seeing in the central and southern high plains areas that are losing their ability to irrigate. Basically, they don't have enough saturated thickness, they can't irrigate any longer. So we need to figure out what's the likely production change with climate change and change in water availability. So this is just a plot showing what areas have already basically had problems, and those are in red, so they already really don't have enough to do high volume irrigation. By 2050, it's the areas in yellow. By 2100, it's the areas in green, leaving basically the white areas that can irrigate after the end of the century. So we combine this, and now we look at the projected crop production, climate change plus water availability. Now, under any of these scenarios, you see dramatic declines in production. This is a big deal. This is a big concern, given this is one of the key breadbaskets of the United States. So what you're seeing is there's a shift from irrigated declining. There is some increase in dry land because, of course, if you go out of irrigated production, what are you likely to do? You're likely to go into dry land production or go into range. So that is for corn. And again, the story is much less dramatic for wheat because of the CO2 fertilization. So you're seeing basically fairly stable yields in the dry land portion and some reduction in irrigated yields, but not very much. So the last couple slides, we're doing regional crop modeling on a NEPA-funded project where we're going across the entire Midwestern United States, effectively the entire Corn Belt, to try to understand the same kind of implications that I just showed in the High Plains Aquifer. We're also doing precision agriculture, so using drones and high-resolution remote sensing to really understand at a detailed level in fields if you apply different level of water and nutrients across a field, how much better can we do? How much more efficient can we be with water and nutrients and still produce the same amount of crop and also have less environmental implications? So in summary, the Central High Plains and Southern High Plains are clearly very far from sustainable. Decline in storage of about 400 cubic kilometers, to put that in perspective, that's about the volume of Lake Erie. So that's a lot of water. Irrigation alters regional climate, and it should definitely be included in these regional climate models and also hydrology models. Climate change is going to exacerbate our water and food production challenges. As you see, irrigation across the Central and Southern High Plains is going to decline because of water availability, and that will lead to reductions in crop production. So this is leading into this NEPA project that we're working on now, which is helping develop climate, nutrient, water smart technologies that couple these high-resolution remote sensing products with process-based models. So with that, I'd like to thank you, and if you have any contacts, send here.
Thanks very much, David. Let's take a couple of questions. Right beside you.
So what would it take to do the same thing for California with all the specialty crops and perennial crops?
So the model is developed to do all of that. In fact, we use things like the cropland data layer, or as we saw at an earlier presentation here, if there are maps of what the actual crops are, we can apply these same technologies here. In fact, we have a proposal pending that would do all of the main irrigated areas of the United States. So hopefully that gets funded and we could work here.
There was a question right at the front here. Yeah, and then we'll go to the back for the last one.
Is your model with the added irrigation package, regional, global, calibrated or not?
It is the only piece where we do calibration is in a groundwater model. We have to calibrate hydraulic conductivity because there's generally not enough information. And there's a component of the irrigation module that is not well understood, which is basically how much water do you actually lose from where the spray is to the ground. There's a huge amount of data, but the drift coefficient that's associated with that is really kind of all over the map. So we're going to have to do some really detailed work, and it's probably going to involve some calibration and looking in the detailed data to get that component right.
There's one at the right over there. Thank you.
Probably you'd answer the question already, but just follow up. It's very interesting to see, David, your results and an effect of irrigation in the climatic model, especially that caught my eye. Do you see that evident also in the observations in the region, like could you find some correlation between irrigation going up in the last decades and then temperature changing and precipitation changing in those regions?
So we've done a little bit of comparison between our models and data in these two papers that we've published, and there is some indication that that's occurring. One of the things that we like to do is actually really look in that whole concept in much more depth. I mean, one thing that's really difficult with climate data on its own is to say, what do you actually see as trends, right? Because there's so many things that cause variations in the actual climatic data. But there are some linkages between what we're seeing in the climate model and the data.
We have one more at the back there, I think, and then we'll...
Thank you. This is really powerful, and I appreciated it. I live in a world with one state, and I know how I would use this information to take to one state, but you're dealing with how many states? So what are the steps to get this in front of the policy, legal framework, people who need to be coming to terms with this?
It's an excellent question. So we're doing about 8 states in the High Plains project, and we're doing many more than that, basically, again, the entire Corn Belt. So what's a way to get that in front of people that are making choices? Well, one thing is conferences like this. Taking that next step and turning these things, really getting in front of the people that are truly making all these decisions, I wish I knew the answer to that. We are in academia, and mostly we're trying to write papers and present to people that hopefully are going to take that next step or get us in touch with people that are.
Let's thank Dave for a stimulating talk this morning.